Hello, Rouse. For lesson 6.6, we are going to solve some exponential equations. And we get pretty excited about our new tool of logarithms that lets us solve all sorts of exponential equations that we couldn't solve before. But the thing about logarithms is that they're an advanced tool, like the quadratic formula or the factor theorem. You don't want to use this tool until you need it. So make sure you exhaust all of your other options, because jumping into a logarithm is usually not the best approach until you've tried your other options. For example, in this equation, if I'm trying to isolate x, I can kind of build an onion here and undo some of these operations without worrying about logarithms. I think at least I can isolate this power pretty quickly. I can undo the subtraction with a linear operation of addition to both sides. That would give me 2 times 4 to the exponent 3x minus 1 would equal 16. Make sure you don't do 2 times 4. 2 times 4 is 8, but there's no 2 times 4 here. This is 2 times a power of 4. And BEDMAS would suggest that I would have to evaluate the power based off of this exponent first. Right? We know this to be true. We know that 2 times 4 squared, which is 2 times 16, is 32. We know that that's not 8 squared. No. Okay. Yeah, so I mean, I could take a logarithm of both sides right now, but I don't think I need to, because I see I have a multiplication of 2 that I can undo by dividing by 2. Division is not distributive across products. I'm just going to divide that by 2, and that'll take care of it. I don't need to divide the 4 to the exponent 3x minus 1 by 2. If I were to do that, it wouldn't just be 2 to the exponent, whatever. But so I have 4 to the exponent 3x minus 1 equals 8. Now, I suppose I could take a logarithm of both sides right now. But again, I don't think that I need to, because the base of 4 and the base of 8 could both be written as a power of 2. Let's use our grade 11 skills of trying to write both sides as a single power of a common base, using my grade 9 skill of simplifying a power by keeping my base and multiplying my exponent. And then the argument goes, if I can write both sides as a single power of a common base, then my exponents must be equal to each other. What I want to see is, when you're using this approach, make sure that you have both sides written as a single power. A lot of students jump from here to, 6x minus 2 equals 3, and I don't see that to be true. Okay, then I'm back to a linear equation, which I can solve by undoing operations in a reverse BEDMAS order. We don't want to try trial and error here, because it turns out the solution is 5/6, and I doubt I would have tried an answer of 5/6. Now, where would logarithms be useful? From the very start, not so much, because I don't have a property for a logarithm of a difference. I know a property for differences of logarithms. That's a difference of logarithms is a logarithm of a quotient, but this is a logarithm of a difference, not a difference of logarithms. So that's a bad idea. I also didn't take the log of both sides. There. No. Could we have used log properties from here? Probably. Log of 2 times 4 to the exponent 3x minus 1 would equal log 16. Then I would write this as log 2 plus log of 4 to the exponent 3x minus 1 equals log 16. And I would subtract. When I subtract both sides by log 2, though, notice I have a subtraction of 2 exponents. When would I have subtracted my exponents? When I divide my powers. So it kind of raises the question, why didn't we just divide both sides by 2? Why would we feel the need to use a logarithmic property? It demonstrates a misunderstanding of a much more efficient approach. Now here, perhaps, if we're not seeing how 4 and 8 can be written as a single power of a common base, this is where it becomes less silly, let's say, to use log properties. From here, we could have taken the logarithm of any side. We are allowed to take log of any base of both sides, though. If you left it up to me, I don't think I would use the common logarithm. I would probably do log base 2 of both sides, since 4 and 8 can be written as powers of 2. Now, if I notice that, maybe I shouldn't have used a logarithm. Maybe I should have just written both sides as a power of 2. Anyways, if I miss that, here is a power of a power. Let's keep our base and multiply our exponents. Log 4 equals log 8. And then I'm going to isolate for x by undoing these operations. I'm going to divide both sides by log 4. This is a division of logarithms, not a logarithm of a division. It's a quotient of logarithms, not a logarithm of quotients. There is the change of base property, which we'll either talk about very soon or perhaps we have already talked about. And then I would add 1 to both sides. So I'd have log 8 divided by log 4 plus 1, and then divide both sides by 3. Or maybe I multiply by 1/3 so that I don't get another fraction in there. Right. Now, I guess this is kind of the challenge, is because I don't see that this number is going to be 5/6. I might have to look really, really carefully here and see that I could switch this to log base 2 of 8 divided by log base 2 of 4, which is going to be 3/2, and 3/2 plus 1 is 5/2, and 5/2 times 1/3 is 5/6. Now, I might have to resort to a calculator, which might not give me an exact answer, depending on how new my calculator is. Let's try 1/3 times log of 8 divided by log of 4 plus 1. And yeah, my calculator can't convert that to a fraction. So if I was expected to get an exact answer, which I see no reason here why I should have approximated, using a logarithm kind of leads me down this pathway where I might lose the precision, the exact value. Okay. It would not earn full marks because it is not an appropriate use of the tool at an appropriate time. Just like if we could factor by grouping and we use the factor theorem, it demonstrates a lack of understanding of factoring by grouping. Right? If you're using the quadratic formula to solve a quadratic that you could solve by factoring, that doesn't demonstrate a mastery of the quadratic formula. It demonstrates a lack of understanding of factoring. Now, I was going to do another example. I guess I still will. Very similar to this, but it's going to feel very familiar because I'm going to feel the need to use a logarithm. Let's just talk about the difference here. So can we see both at the same time? There's the original. 2 times 4 to the exponent 3x minus 1 is equal to 15. And here I just switch that to a minus 2. So what's the big deal? Well, I still don't think I would start with logarithms because I'm seeing linear operations that I can undo. I can undo a subtraction of 2. I can undo a multiplication by 2. And everything is fine, just fine, until I get about here. And then I see, well, I can't use my grade 11 skills. I'm having a hard time writing both sides as a single power of a common base. So now seems like a good time to, it's going to mirror this solution right here, take a logarithm of both sides. And I'm not seeing an advantage of taking log base 4 of both sides or taking log base 17/2 of both sides. I think I'm just going to stick with the common logarithm, a logarithm button that my calculator has here. Then I use my log property, power of a power, keep my base, and multiply my exponents. This can be written as log 17 minus log 2. I'm not seeing why that would be useful. And now I am going to peel the operations off, the operation layers off of this equation onion. I'm going to undo a multiplication of log 4 by dividing both sides by log 4. That'll give me log. Okay, I do see maybe one reason why I might want to write that as log 17 minus log 2. It would avoid fractions over fractions. But it's not, I mean, yeah. I don't have much to say about it. I'm going to add 1 to both sides. Log 17/2 over log 4 plus 1. And to avoid fractions over fractions, let's multiply both sides by 1/3 instead. log 17/2 divided by log 4 plus 1. Okay. Directions for a lot of equations like this would say give an expression for the exact value. There it is. Followed by an approximation. I usually say to the nearest hundredth or thousandth, just to discourage students even more from doing trial and error. Let's try 1/3 times bracket log bracket 17 divided by 2 bracket divided by log 4 plus 1. Close that bracket. And I get about 0.848, I guess. Let's try it once more, because there's a lot of places where I could have made a mistake. I'll do 17 divided by 2 equals, the logarithm of that equals, divided by log 4 equals, plus 1 equals, divided by 3 equals, and yeah, I get the same number. Oops, sorry. There you go. Okay. There are more challenging examples than this in our lesson and in our homework. So make sure you seek them out and try them out. Just don't, when you focus on the difficult ones, you're going to be using logarithms a lot. Don't be in a rush to use them. Do what you can first. Okay? Try it out.